Okay, the last part of chapter 15 is going to deal with what's called Le Chandlier's principle, good old French name. And this is if you do something to the equilibrium to disturb it. Like if you change the temperature, the pressure, you add more reactant, you add more product, something, you add a stress to your system, the equilibrium is going to shift. It's going to counteract and it's going to come to equilibrium again. But it might happen like when you did the activity with the coins, if you added more reactant in the beginning, eventually you're going to come to equilibrium. It's just going to happen a lot. It's going to take a while longer, or it's going to happen when you have bigger numbers. Okay, so here's some of them. This isn't the best chart, but you can see some of the things that are going to happen. And you can read through this. It talks about temperature, endo and exothermic. I actually have a good chart for you. When you do the assignment for this, there's a really good chart that explains it all. And that probably is a little bit better than this diagram. So again, things to remember when you're changing, when you're adding reactant, it's going to shift to more product. When you're adding more product, it's going to shift to more reactant. So there's things that are going to happen in order to get equilibrium again. Okay, so if you change your reactant or the product, if you change their concentration, so the system is in equilibrium and then you add some reactant. Well, now what's going to happen is you're going to reach equilibrium again, but it's going to be at a different level. Okay, so here you can see we have our initial reaction. We have H2 here. And we have H2 and N2 and we're making N3, I think it is. Yeah. And they were at equilibrium. Well, then if I add more H2, I add more of one of the reactants, what's going to happen is now I'm going to move the equilibrium up. It's going to be at a different level. So anytime you add a reactant, it's going to shift, so it produces more product, and then it's going to reach equilibrium. Okay? If you change the volume or the pressure, okay, now remember, we're working with gases. When we do equilibrium, we only deal with gases. And so if you change the volume or pressure, you're going to have an issue with your equilibrium. So a change in pressure volume will affect your equilibrium. Higher volumes, lower pressures favor the side of the equation with the more moles. So if you're looking at an equation, let's say you start out with 2 moles of reactants and you end with 3 moles of product, it's going to favor the side with the 3 moles. It's going to favor the side with the most. And again, I'll do that chart that I have for you. It explains this a little bit better. Maybe I'm confusing you. I hope not. If you're changing the temperature, it matters if you're starting with an endothermic reaction or an exothermic reaction. It's really important, okay? If it's an endothermic reaction, heat acts like a reactant. So if you change the temperature, the adding heat is going to drive the reaction toward the product. So anytime you have an endothermic reaction and you add more heat to it, raise the temperature, it acts as a reactant, which means it's going to drive it so that you produce more product. If it's exothermic, again, heat acts like a product, okay? Because it is one of the products, if you remember when we write those out. So if it acts like a product, so that what's going to do to get equilibrium, it's going to drive it more toward the reactants. So when you have an endothermic reaction, when you add heat, remember it acts like a reactant. And again, remember when we wrote out the problems, we always put, if it was an endothermic reaction, we always put the energy on the side with the reactants. If it was exothermic, we put it on the side of the products. So that kind of makes sense. Okay, here shows it to you. The change in the color because of equilibrium. And again, this is an endothermic reaction. We got the heat over here. So it's going to drive it so you produce more of the blue color. Okay, and again, you can go back and look at these. I'll put this PowerPoint on, but I have probably better things. Okay, so when we're looking at an exothermic equilibrium, and again, we go back to the Haber process, the process for making ammonia. It's, a big deal because it's a common thing. One thing you'd think if you cool down the reactants that you would end up with more product, but that's not the case because if you do it too much, because you're thinking, okay, so I want to cool down the reactant so it can produce more product, because that's a big thing. You're making product, you're making money. But if you get it too cool, then you have a problem with your activation energy. Remember, there's an energy you have to overcome for a reaction to start. So you have to be careful when you're trying to manipulate your equilibrium. You can't mess with your activation energy or your reaction's just not going to happen. Okay? So there are some cases where a system in equilibrium can be affected by a catalyst. Okay? And again, a catalyst, remember, helps lower activation energy. So if you're messing with the temperature and you get to the point where, it's not happening because of activation energy, you can add a catalyst, and that will be a stress and change equilibrium. Okay? So catalysts, remember, increase the rate of both forward and reverse reactions without changing themselves. Okay? So sometimes when you add a catalyst, you reach equilibrium faster. The point at which equilibrium is reached is still the same. When you're doing, like when we did our coins with the rounds, and if you reached equilibrium at round 7, it just means that it's going to increase it. It'll make it happen faster, but time-wise, but the equilibrium point is still the same. So like if you reached equilibrium at round 7, now you might reach equilibrium at round 5. But the amounts of the reactant and product are still the same. Get out of here. Sorry, dogs. Okay, so the reason why catalysts do that is a lower activation. So the thing, if you add a catalyst, if you add something, it's going to make the reaction happen faster. You're going to reach equilibrium faster, but the amounts of reactant product are still the same. You're not going to change that. Okay, so what I did, again, this is similar to the chart that you'll see that I made. If you add reactant, then it's going to shift toward producing more products before you reach equilibrium. Okay, if you remove some reactant, then it's going to decrease the amount of product. In other words, you're going to get more reactant. If you add a product, it's going to move toward the reactant. If you remove a product, again, it's going to, so this is how it shifts, okay? And again, this is the stress over here, and this is what happens when you stress. Okay, if you decrease the volume, okay, the side with the least gas particles are going to be the one it's going to shift toward. And I'm talking about the equilibrium, okay? So again, when I'm talking about volume and least gas particles, you're looking at the moles, okay? If you have, 2 moles of a gas plus 4 moles, those are your reactants. That's 6 moles on your reactant side. And then on your product side, let's say you end up with 3 moles. Okay, so you've got 6 and 3. The one with the least gas particles would be the product side with a 3. The one with the most would be the reactant side. So when you're looking at volume, you got to look at the moles. Okay? Okay, so to summarize Le Chandeliers, if you have an endothermic reaction, again, one that's absorbing energy, energy is like a reactant. If you have an exothermic, energy is like a product. So if you go back here, when you're looking at this, remember, temperature-wise, if it's an endothermic reaction, I'm adding a reactant, I'm going to favor products. Okay? If it's exothermic, okay, that's a product basically, then it's going to favor the reactants. And when I say favor, it means shifts more so that this number is higher to get the equilibrium. That's what it means by this, okay? Anyway, so anytime you increase the temperature for an exothermic reaction, you're going to get more reactants. Anytime you increase the temperature for an endothermic, you're going to get more product. Again, it's like adding more reactant when you do an endothermic. It's like adding more product when you do an exothermic. And again, you can look at that, and I have this on that chart for you, so you can just look it up. Okay, there's some things that don't affect equilibrium. Okay, you can add them, subtract them. It won't affect equilibrium. Adding and removing a pure solid or liquid, we talked about that. The only thing we deal with are the gases. Okay, if we have a non-reactive gas, okay, sometimes you'll have those in there, like noble gases. They don't react with anything, so you can put helium on both sides. It won't matter, okay? If we change the volume of a reaction with equal number of gas particles, so if we have 2 moles of gas particles on the reactant side and 2 moles of gas particles on the product side, if you change the volume, it won't matter. Okay, so if the moles of gas are the same on both sides, changing volume is not going to affect equilibrium. If you add a catalyst, remember the catalyst makes reaction happen faster or slower, but it doesn't change equilibrium. It just makes it happen faster. Okay? So what things affect the equilibrium constant? Of those things I talked about, temperature is the only thing that affects an equilibrium constant. We're talking about volume, pressure, and so on. Temperature is the only one. Okay? If you increase the temperature, again, of an endothermic reaction, if you're increasing the temperature, then you're going to increase your equilibrium constant, okay? If you increase the temperature of an exothermic reaction, you're going to decrease your equilibrium constant. So the one thing that affects the actual equilibrium constant, because the other ones, you're just changing when it happens, but the actual affecting of the equilibrium constant, the only thing that affects it is temperature. Okay, so here's an example. How am I doing time-wise? I'm doing time. Okay, so here's a reaction. We've used this reaction before, and it's plus 92, so this means it's a endothermic reaction. Okay, so if I have this and I increase it, what it's going to do, if I increase my reactant, I'm going to increase my product. So it shifts toward the right and it favors products. And one thing to remember, if it favors products, it shifts to the right. If it favors reactants, it shifts to the left. So they're always the same. Okay, so I'm increasing my reactant. It favors the product. I'm going to produce more product before when I get to equilibrium. Okay, if I increase my product, okay, I'm also going to increase my reactant. But this is going to favor the reactants. So now it moves to the left. So they're just the opposite. If temperature is increased, now this is an endothermic reaction. Okay, if temperature is increased, I'm going to decrease my amount of reactant and I'm going to increase my amount of product. So it favors products, it moves to the right. If I decrease my temperature, just the opposite. Increase, decrease, left in reactants. So again, looking at your endothermic or your exothermic determines what happens. Okay, here's another example. And again, I'm not going to worry about the solid and the solid. All I'm worried about is this gas. Now here, it's on this side, so that means it's an endothermic reaction. Okay, so these guys, if I add those, there's no change. Okay, if I add CO2, that means I'm adding product. That means I'm going to shift it to the reactant side. Because anytime you add product, it shifts it to the reactant side. Okay, if I remove some of this, now I'm decreasing the amount of reactant, I'm favoring the product. Okay, again, temperature is decreased. I'm lowering this. This is an endothermic reaction. Remember we said if we decrease the temperature, okay, we produce more. It's going to favor, equilibrium is going to favor the reactants. If we increase the temperature, again, that's like adding more reactant, that's going to produce more product. Okay, and then I put a catalyst in here. And again, catalysts don't change equilibrium. Okay, they just change at what point it happens. It just happens faster or slower, but they don't actually change equilibrium. They just make it occur at a different rate, but the actual equilibrium is the same. So here again shows you, but if you have solids or liquids, you guys, they're not, you can change them all you want. It won't affect equilibrium. Okay, so, and I have here's another one. I'm looking at my time here. Okay, again, we got a solid here and a solid here. So all I'm looking at is this guy and this guy. Okay, there's not going to be a change if I add pressure or volume. It's not going to be changed because look, I got 4 moles here and I got 4 moles here. It doesn't matter the solid. So if I have the same amount of gas on each side, it won't, changing the volume isn't going to affect it. If this was 3 and this was 4, then there'd be an issue, there'd then be a change. But when you have the same amount of moles on both sides, it won't affect it. Okay, same if you change the pressure. Because you have the same amount of moles of gas on both sides, it won't matter. Okay. Now, if you change these two guys, it won't matter either because they're solids. And solids and liquids don't affect equilibrium. Okay? Okay, a catalyst won't change the system either. So the only thing that can change this equilibrium, because you've got the same amount of stuff, would be temperature. That's the only thing. Okay? And then you'd have to determine if this is an endothermic reaction or exothermic reaction to see what its changes would be. Okay? All right. So that's equilibrium. We're done with chapter 15. After you do your Le Chandeliers, remember to print out that one that has kind of a cheat sheet for you. Do your problems. Then I'll also have a review for you to help you with these type of problems that we did for this chapter. So we are done.